Alrighty then. Hey guys, what's going on? Memes here. Yes, thank you for joining me late night crew from wherever you happen to hail from on the internet. Whether it's on the YouTubes, the X Twitters, you're coming in from the skies are so blue, the Discords, or for some reason the algorithm thought you might be interested in time current squared. So what the heck am I talking about? What the heck I'm talking about is yesterday while we were discussing some different stuff and things, I all of a sudden noticed there may be a wee bit of a pattern. See you there, and competitors. Thank you for joining, my friends. Yeah, so basically yesterday we were having a bit of a discussion. It's like, oh well, what is this? I realized you could rewrite some of these things on the board in different ways, and it's like, wait a second. Gap! Gap, good to see you, my friend. Good to see you, Captain Coldpile. I enjoyed our talks many ages. Wow, I'm an old internet troll, aren't I? But good to see you guys, my friends. All right, so we're going to be talking about tonight. Don't worry, we're not going to do crazy. I understand. There's some magical symbols on the board. Just imagine me as a slightly tall dwarf, missing the impressive beard right now, and I'm carving some rune symbols with a with a magical. Okay, I'm trying to go a little too far Tolkien there. Uh, all I'm saying is different stuff can be rewritten in different ways, and depending on how you look at something, you're gonna interpret it different. You ever see one of those things where they have the shadows and everything, and you're like, "Oh, obviously that's a circle," and then they turn it around, and it's like, "Yeah, that circle you had there, it was actually a can jar of nuts. Yes, fancy cashews." It's empty. It makes me sad. But it's about perspective and everything. So if you were to just shine a light, it's kind of like back in Plato's cave and stuff. If all you saw was the shadows and outlines, you're going to get a particular perspective on the world. You actually get to pick stuff up and look it around and feel it, maybe give it a smell, maybe it's edible or something. Some things you shouldn't put in your mouth. That's how you learn. Eventually, yada, 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 what is it? Natural selection, something like that. I don't know. I ain't Darwin. But what we're talking about today is okay. So in the description, it has the fine structure constant and the Ampere constant having cost come. Hey, Grizz, good to see you. Don't, don't square my current, bro. Yeah, well, apparently it's actually really important. I literally didn't notice until I was writing out things. I'm like, wait, what? So then I had to write it all out, and then I had to send a picture to Thad because I'm like, I don't know, maybe he probably knew it or something, but it's just a different way, especially if we're trying to figure out what's going on. And hydration is important, my friends, especially when you ramble as much as me. Where were we rambling at? Back to squaring the current or time current. See, that's the thing. What is time current? Okay, we're going to start at the end. Why? Because that's what I just said. All right. Time current. So these notation here, you see all these fancy things. All right. The crazy fish symbol over here, that's alpha. That's for the fine structure constants, basically the strength of the electromagnetic coupling. It's like not 0.00729 yada yada yada. So it's basically the James Bond of constants of nature. All right. Uh so this number here, that's the number as I'm pointing at the E. No wonder people lose their minds. Anybody doing math or science. The number E, number one, that is a number that makes it more confusing. This version, it's okay. It is a number. It's a measure of charge. It's elementary charge. So basically, the charge of an electron or a proton, because one's negative. Our convention is technically backwards because good old Ben Franklin at one point, he's like, you know what? I mean, there's a 50-50 guess. I'm going to assume this electric thingy, I'm going to assume that's negative. Why? I don't know. If I was flying a kite up there with a key on, I get struck by lightning and I'm getting zapped and everything, I'm going to view that as a very negative circumstance. Just a personal opinion. An electron or current convention, it's negative charge. A proton is positive charge. But that little caveat aside, basically an elementary charge. Okay, what's this QP? Anything with a subscript P there, that's a Planck thingy. What is that? The boundaries of existence or persistence, at least for us. All right. So it's either going to be a minimum or a maximum of the five elementary bases: time, space, charge, mass, and temperature. Okay. When those five ingredients combine, you can get the constants in nature. You need to apply some form of a geometric thing to different combinations of that five-dimensional stuff. Okay. So you see, I think I'm getting maybe a little bit better at explaining these things. It's Professor Wolfram just finished like a 2-hour talk about like his minimal proof for the axioms of piano arithmetic. So your basic, I think it's the basic algebraic structure and stuff of logic. So the bases of logic he has as this proof that he's like, yeah, nobody understands what it means. It's true. We don't know why it's true, but essentially it's able to. We're not getting into that because that was really confusing. At least here we have fish symbols. All right. Called for the elections are negative. Well, it's yes. So here's the interesting thing. Oh, that is interesting. Well, the charge units are going to cancel. I mean, it's squared anyway in this case. So technically it's, yeah, but if it's not squared, it's different. Okay, for that, it would change this. So in this case, it shouldn't matter. Shouldn't. You might get a positive and a negative answer, but technically, I think that is the correct statement. All right. So it's the charge of an electron. All right, I'll just say that. I won't have to say both each time. It just gets repetitive. So the elementary charge of an electron divided by the maximum charge, and that's squared. We've got our fine structure fish symbol there is equal to elementary charge over the Planck charge squared. Okay. Now we have this ampere. That's our constant of current. All right. So why I write it as a little box there because that's what that has, the little box. It's also in like 288 equations to help compute the constants of nature. So there are some additional receipts behind it. But okay, we just use the box right now. What's that? Oh, it's got the Planck mass because we got the little p there. And then we got the Planck length because we got that little p there. We got an m for mass, Planck, L for length, Planck. That's divided by the Planck charge squared. Because we got the little thing on the outside of the brackets there because it's squaring both of those things, but it's only squared here. Why am I showing you any of this? Okay. The reason why is because this is one way of rating the fine structure constant. All right. Here's the normally defined way. You look at it, you're like, all right, what's the difference? The difference is, well, it's squaring both those things in that thingy. And then we just get that thingy and it's squared up there. So we got a charge squared. And like, okay, this ends up being a dimensionless ratio. All right. So that means that this whole crazy thing here, this 4 pi h bar c epsilon naught, is equal to the Planck charge squared. I mean, that's a cool thing. That's what it comes out in Wolfram Alpha too. Okay, so that's cool. I already knew that. When I saw this, I'm like, oh, this is pretty cool. But other folks knew that and stuff. I think John Mackey or no, I think that's a gentleman playing the new Captain America that may have been having a bad day. Uh, but Jonathan McCrack, I forget. Other people know that, but that's a standard definition. People know that. All right, the Ampere constant. Yeah, I've known that for a while. I've looked into that. I found like the craziest conjecture thing that me. If you actually give some layer there, it's some version of space itself might be, I don't know, the 600 cell, basically a four-dimensional platonic solid, or maybe it's intersect with another four-dimensional platonic solid. That's not the discussion for today. We can have that on another day. Welcome, Adam Jones. But thank you, my friend. Hey, it's okay. It's okay. I don't think any of us really know what's going on. I mean, that's probably the ultimate question. I don't know, but I think we can seek to be less wrong. I don't think that's a bad place to start. Uh, Basically, ultimately, we're just looking at some relationships here. And this is something that I'm sure other folks know. I'm sure there's plenty of retired electrical engineers that have known this. I now see where all the draw is, because that's basically like a physicist meme. They're like, "Oh, everybody sit down, wait till the electrical engineer is speaking." They make fun of a lot of these people. I'm like, I'm pretty sure there's some really smart retired electrical engineers that figured out a lot of things, and maybe just nobody's listening. I I don't know. I don't know. I'm not an electrical engineer. So, but basically, you have ways to write different notation and stuff, and within the constants of nature, from the dimensions of measure that we can measure, you can boil down to five: time, space, or a derivative of length. So whether it's just a single dimension like a to b, whether it's an area, which is length squared, or it's a volume, so it's like length cubed. So you got time, space, you got charge, mass, and temperature. The thing is, you can also rewrite those or express those in different ways. And by looking at the different combinations, we may be able to gain some more intuition onto what might not be going on. And full disclosure, I'm not a licensed quantum mechanic. I I've never actually, okay, maybe I can't say I've never finished a physics class. I've done like radiation and life. I took like modern physics in college for all of like 1 week and a half, and I took it because it sounded cool. And there were, I never took physics one, two, or three, the labs, electromagnetism, thermodynamics, or anything. I may be the luckiest son of a gun in the world, but hey, good to see you, Jax. Welcome, my friend. No, just a little late night session, just describing some different relationships, and we'll get the time current. Okay. So since I said we are starting with time current, I mentioned it briefly and then went all the way back to the beginning. Okay, we're back to Ampere's constant right now. Basically, what is that? Basically, the unit for the amp, the constant for amps or amperage. Because one of my electrician friends says, and again, this is a quote here. It's not the voltage that gets you; it's the amps. Like you see Nikolai Tesla, a million volts. Oh my God, how is he doing that? It's very low amperage. Yeah, I'm not a doctor, but basically, this whole boundary of charge, so the maximum of charge per some form of a unit basis, but squared is equal to 4 pi. So that's, look at that, like a sphere. So we got like a sphere thing. So we got a sphere thing. H bar is the elementary unit of action thing. So we got a sphere thing acting. Z is the speed of light in a vacuum. So we got a sphere thing acting at the speed of light. And then epsilon naught, which is the the electric permittivity of free space. All right. So that means we got a sphere acting at the speed of light, electrically at the permittivity of free space. Is that all? Okay, so in my mind, I've got basically like some like electric charging sphere, kind of like a Rasengan or something from Yu-Gi-Oh! And it's kind of acting, and it's going really fast, and it has the ability to permeate and do whatever magical thing it's doing there. Um, oh, and since it's an app, it's a mass distance. So this would be a mass distance divided by a sphere acting at the speed of light via the electric permittivity of free space. I have no idea what I just said. Okay, I could repeat the words that came out, but to actually gain an intuition of what's going on, I am open to interpretation. I am sure there are folks out there, but all right. So you've basically, okay. The way to actually break this down into a way that actually makes sense is, oh wow, I didn't even go into the whole dang thing I wanted. Oh, I need to add something. That's why I'm missing it. That was a little thing over here. Okay. This is also equal to MP. Sorry, it's going to be a little squished. MP, P over T P squared I P squared. Okay. I knew there was totally something missing there. All right. So why did I rewrite this again? Okay. Because when you get down to this, which okay was actually the next line, that's the Planck charge squared. So it's basically a maximum of charge squared. Okay. And that's equal to that 4 pi h bar c epsilon naught. So that sphere acting at the speed of light for via the electric permeativity in free space, whatever that means. Okay. Well, that's equal to time, Planck time times the Planck current squared. Okay. So time current squared. See what I did there? All right. So we've got time times current, and that's squared. Okay. I'm not just making parody jokes the whole time. Okay. The reason I'm showing you this is because you see this guy up here. We've got mass times length divided by time squared and current squared. Okay. The reason I'm bringing this up is because if we've ever heard of the whole, you can basically derive all of physics from F equals ma. Why? Because if you get uh, F equals mass times acceleration. Okay. F equals ma. Yes, I wrote it there. What's the purpose of that? What's mass times acceleration? All right, so mass, we could write this as mp, or in Planck units, mp. Then we need a distance because acceleration is a distance. So we'll do Planck mass times the Planck length over time squared, aka TP squared. Okay. Acceleration is length divided by time squared. So this equals the Planck force, F sub P. Okay. We got the Planck force. Wait a second. I know it's there we go. So got the Planck mass times the Planck length divided by time squared. This is the Planck force. The force Planck. Very interesting. Wait a second. Planck mass times Planck length. Planck mass times Planck length divided by Planck time squared divided by Planck time squared. The Planck force equation right there. What? But it's the force divided by current squared. That's pretty neat. And again, nothing of this is new at all. This is just for me trying to think about like what's going on here. I'm like, all right, this same dang expression, this whole charge squared is a sphere acting at the speed of light via the permeativity of free space. All right. That's cool. What's it doing? Well, it's dividing up this magical thing right here, the Planck mass times the Planck length. So a mass distance. It's dividing up a mass distance. Okay. And it's got this current thing going on here. All right. That's so you've got a mass traveling via current. I don't know. That's little pipes in the head or something like that, or imagining the charge traveling along. And apparently, the way a lot of things actually work is different than we thought. 'Cause before it's like, oh, they're just showing all the electrons on and stuff. It's like, no, all you got to do is jiggle the electron, especially with alternating currents, to just get them to vibrate. That's also where we get like a lot of the heat, apparently. But as you're doing that, you're actually putting a little like causing excitation, the electric field. And that's why that Veritasium video from a while back, it's like, all right, you flick on the light switch, how long will it take the thing? It's like, it goes on about the speed of light. It's like, wait a second. The electron should only go at about 137th the speed of light, or about the fine structure constant times that. Uh, but apparently, yeah, it goes very close to C. That's a very interesting thing right there. So every time we see something like the Planck charge squared, we can think of it as a sphere acting the speed of light via the permittivity of free space. And that's just something where it's like, huh. I mean, I kind of knew that. And then it's all said, it's like, oh, yeah, time current squared. Time current squared. Sounds like things are like whirling around and everything, or I feel like that should be a sci-fi sitcom or a TV show or something like that. Maybe kind of like the new Quantum Leap. It's like time current squared. What happened to the first derivative? Don't you mind that? It's be the prequel. Hey, K Shell. Good to see you, my friend. Good to see you. Now we're just talking the finer stuff of different things that I had noticed yesterday, and let's go through and just make sure I'm not just talking out of my butt. We'll do that. I'm not sure I want to know which show they remade. Wait, was it Quantum Leap or I forget what I said. Did I say Quantum Leap, Babylon 5, or Stargate? Because I feel like I meant to say Stargate, but yeah, a lot of remakes usually don't go all that well. Not necessarily all, but yeah, some of them aren't really up my alley. Let's put it that way. All right, so where were we at? Let's can share the other thing. I'll go back. This window. Don't mind any of the massive temperatures or anything. New window. All right. So what are we doing here? Alpha. Okay, so let's do this. Then watch so quantum leap, right? Oh, you did try to. I heard the. Did I ever watch the first one? I know I watched some of Stargate back in the day, and I remember at least some of that stuff seemed pretty good. Quantum, I don't think I ever got. If the original is worth watching, I might do that. I feel like I need to watch that like Firefly. All right, so we're at all right. Momentary charge over the Planck charge. Let me square that. This should give us number right here. Is a number equal to unstructured constant? I found at least the other day it still does round for a bit, but trust and verify. What was that number? Let's do it right here. All right. What's the number if we just look it up via the good friends at Wolfram's database? All right. That looks like the same number. That's this crazy expression that we got on the board right over there. That elementary charge over 4 pi h bar c epsilon naught. Yeah, we got elementary charge squared over 4 pi c epsilon naught h bar. Okay. They write it a little bit different. The commutativity holds, my friends. It's just multiplication in our standard math, so reasons. Maybe Professor Wolfram's axiom explains that. See, electromagnetic coupling. All right. Yes, no, I have not watched. I'm a big sinner. All right. Gay Shell is recommending the original Quantum Leap. Okay. So I feel because I was never really a huge sci-fi dude back in the day. Like Star Wars was pretty good. I watched some Deep Space Nine back in the day. I'd watched a good bit of Trek at the Physics Monastery just because it's a Trek. It's adventures in space. Some Treks are better than others. Okay. But where are we right now? Okay, so I got this thing, and then where were we going? All right. So just so just so I'm not just pulling things out of my butt. All right. So I'm gonna write it out there. Uh, Boom. All right. So we got our thingy there. All right. I find you got to actually write out elementary charge. Elementary charge squared over all that jazz. Okay, because it's those digits again. See, not 007. Boom. All right. You're gonna actually want more than 007, but just saying. All right. So the question is then, what happens if we pull out that elementary charge? Oh, let's just do this. What's our other expression on the board? Hold on. This is the Planck mass times the Planck length. Let's try that. All right. So I'm gonna do the bracket Planck mass Planck length, and yeah, it's not squared. All right. So we divide it by that stuff. Oh my god, we got like a 10 to the minus 7 there, and we got our 1 Ampere constant. Groovy. So that thing is, this crazy thing is charge squared. Ain't that groovy? All right. Well, let's change it. Let's change it to its other form because it's the time current. Dun dun dun. So what does that mean? All we do is like time, like current. Go outside the bracket. We square the whole dang thing. Let's see what happens. Oh, look. Okay, so since the Planck time, the Planck length, we only have 5 significant digits to that. It it can only give us so many significant digits. Now, I think here's the problem with Wolfram Alpha, because if I do equals find structure constant, it's got about 4 significant digit. Uh, Equals? No. Convert 1 alpha find structure constant to 2. Uh, it's responding as true, but it should. Yeah. It shouldn't be returning true because I mean it holds for 4 significant digits. Um, but yeah, that's that little thing. So when it gives me that little return, it's like this is true for our expression with the Higgs boson mass. I'm like, we really don't have enough data there to say that because I mean, there's only 3 known digits to the Higgs boson mass. It might match for 3, but honestly, we can't say that that's an equivalence because we need more scientific data to really be able to say anything. Uh, so that's why I submitted a ticket because I need to argue against something that supports my case, at least memetically. Because that's science. You don't want to say things that aren't true. Uh, where were we? Okay, so we swapped over time current. So let's swap over back with our other friend. Planck mass, the Planck length. Use some building blocks divided by our time current squared. Okay. Oh, look, and we're back to 1 amp constant. Gee golly, Charlie Brown. So it's a mass distance divided by time current squared. Okay. Or in that place, if you do it on the outside, see, that's where the brackets are important because otherwise it's time squared, current squared. That doesn't sound anywhere near as cool as time current squared. It makes me happy. It makes me happy. Where are we? Yes, 0029 something. Why is my H bar in the wrong spot? Because it's mathematics, so if you multiply, it's the whole they call it commutativity in math, so it's like I can do 5 times 3 times 5 times 2. Okay, I can do that. But then if I move, hold on, I need to remember the number. All right, 150. I can put the 2 over here, and we're gonna get 150. I put the 5 over here. I get 150. It doesn't matter the order. If you start getting up to like octonian numbers and stuff like that, yes, the order does matter because some things are non-commutative, aka the order matters. But for like a lot of the basic stuff like we have here, um, yeah, as long as it's within the brackets, it's gonna go in the order that it's expressed in. So that's like this could be a 3, this could be a 5, but you could put the 5 over here and the 3 over here. Yes, I'm just saying you can move them there. I just if there's a space, it considers its multiplication just for ease there, and I also don't want to have to put the dang little apostrophes there, and occasionally you solve for x because you can put just like an x there too. Excuse me, an x there too. But sometimes you're solving for x, so it can be confusing. So the little star is better, or just a space. Because Wolfram Alpha is like, all right, if you're doing a lot of computational stuff, you might not want to have to keep on doing more notation, more notation, more notation. You're wasting valuable keystrokes, my friends. All right. What was I rambling about? Oh, that basically this whole this whole time current thing, or at least over here for the Ampere and everything, it's basically a Planck force and then divided by current. Oh, that's a good question. What's the Planck force divided by current? Planck force divided by Planck current. Should be current squared, shouldn't it? Huh. And then the 18, magnetic flux gradient. Well, that's interesting. Oh, yeah. That does give us the Ampere constant. Planck force divided by Planck current squared. Why do I feel like I should be noticing something else? I feel like there's something right in front of me that if I was an undergraduate physics student that had actually gone through a full electromagnetics class or electrodynamics, I feel like I would just be going duh right now. Yeah, the dimensions come out, but force divided by current gives us amps or current squared. So if we just went by normal current, that's magnetic flux gradient. So that beckers the question. That was why I take this whole dang thing. I go forward, and we divide it into this thing. I mean, it's just gonna give us out the same thing, isn't it? Oh, it's going the other way. Oh, voltmeter rating. Oh, that's a negative current. Okay, let's divide into this one. Okay, it gives us Planck electric. Wait a second. Oh, because okay, that's the second derivative. The forces are canceling out. Okay. Ah, because the Planck current itself uh, is that why it has 2 times the Planck force between it? Because it's assuming 2 bodies? Uh, I just started watching uh, electromagnetics course, college course, I think from the University of New Mexico. And they were going over the like the units and stuff. And I'm just like, all right. The point they start talking about vectors and stuff. I'm like, all right, well, you're saying, all right, this is going this way, this is going this way, it's going to affect this way. I'm like, all right, there's a magnitude. So yeah, you can do some addition. I'm like, oh my God, I feel like I'm slowly getting a very basic freshman's grasp on it. It's not there yet. What happens? Okay. I like playing, if you couldn't tell. All right. Just because I'm like, all right, if we got the tools and basically the oracles of Delphi here, or maybe it's not the oracle of Delphi, so to speak, but you can ask it a question. And then if it's like, all right, maybe if you don't have this level of experience of having asked Wolfram tens of thousands of questions, you go on to Chat GPT and ask it something and be like, what's the maximum of charge or the minimum of charge or the minimum unit of length divided by the minimum unit of time? Oh, that's like it would be the blank length divided by the Planck time. The minimum unit of length divided by the minimum unit of time, according to our current best stuff and things. And as you see here, it gives you this. It basically says it's the speed of light. There's only 4 significant digits there. Okay. To be fair, it gives you like 6 here. We know the speed of light to 9 significant digits. Why doesn't it give us all of them? Because we already know each of these to like 5. And then we know it's going to come out to at least be the 6th digit to come out to something like that. So that's one of those interesting things. Because actually, we can even do this. We can go to code edit. Not that I visit this all the time. All right. So notice H bar Planck's reduced constant. It is defined at 10 significant digits. Why? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. 10 digits into that 30, negative 34th power, and very small unit of action. The unit of action is joule seconds, basically energy seconds. Oh, let me see. Well, see, that's one of those things where I feel like if you're in class, it's like, oh, duh. Because, like, I'm even listening to the class and, like, I've listened to so many lectures above my head and, like, literally going, like, years. It's like, I really don't understand what's going on. And slowly, it's like, I recognize more of those things. Oh, I can see kind of like that math notation. I know what that squiggly Z might mean. Yeah, that's right. That's right. If it's coming, and the rest, yeah. To be fair, it's just if you're talking about commutativity, basically, as long as the multiplication things are, you can mix them up. You can mix them up as long as you don't go to at least the octodians. Maybe some quaternions. Participation and commutivity may vary. There we go. Uh, so the wild beast. Listen. Some of those toasters, Jacks. There's some brave little toasters out there. I'll tell you what. All right. Predictive text. Oh my god, that predicts so many things, and I'm just like, sometimes it works, sometimes it can be horrific. But let's see. Not Brett. Totally not Brett. Was commenting that that was me today with Gauss' law and a question today for physics too. Thought of electron withdrawing groups in chemistry, and it just clicked. An electron of an electron withdrawing groups in chemistry. It just clicked. Oh my god, it is too late at night. I do not have the mental computation left. I already did my workout and everything. That's the one good thing about if you save your 10-kilometer run at the end of the night, as long as there's not that much traffic around, you just keep going. It's tiring, it might take a while. But yeah, you do that and yeah, the caffeine is worn off probably about an hour or two ago. It's probably better for sleeping. I'll just have my sandwich and hit the sack. What's the case where community? Sometimes for quaternions, so we can just pop over there. So, excuse me, octonians. So octonians. It looks so much like onion. Norm division algebra of the real numbers, kind of hypercomplex number system. Okay. If it's not complex, you probably don't need a matter name for some complex again. I'm not a math PhD by any means. Using boldface an extension. They are non-commutative and non-associative. Okay. So non-commutative is this thing where commutativity, see, depending on which the order there, whether you start with X or Y, you're gonna get out this thing. It's basically gonna be the same, your output. So if it's non-commutative, should probably just non-commutative. Okay. I can always read from Wikipedia. In mathematics, a binary operation is commutative if the changing order of the operands does not change the result. It is a fundamental property. Many binary operations and many mathematical proofs depend on it. Perhaps the most familiar is the property of arithmetic, aka 3 plus 4 equals 4 plus 3, or 2 times 5 equals 5 times 2. The property can also be used in more advanced settings. The name is needed because there are operations such as division and subtraction that do not have it. For example, here's where we start getting 3 minus 5 does not equal 5 minus 3. Such operands are non-commutative, and so are referred to as the non-commutative. So basically, where it doesn't matter, it's commutative. Where it does matter, it matters. I'm sorry, that was not a encouraging thing. I actually just learned that right there. I mean, like, I remember like the basic things going through like fifth, like probably like seventh grade or something like that. It's like, all right, you're doing it in outer the parent. That's why I'm crazy with parentheses, just because like I will put extra layers on there because I feel like it's better to have it and not need it than need it and not have it. Because otherwise, you might get an answer. You're like, oh, there's a fantastic, and then you're like, I made a basic math error. Couple times I'm like, I found something fascinating. I'm like, no, no. I just did an inverse, and the thing I thought I may have been different there, it wasn't. It tell you nothing. Yeah, it happens. It happens. To random their friends and see how you're sponge. Listen, Jax, here's the thing. I spout a lot of nonsense already. Maybe it would help things. Um, to be fair, oh yeah, no, 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 no. If your friends are cool, he's had this coming for a long time now. This is what I was. Yeah, yeah. We all have a lot of different trauma depending on where it was. It's like, see, for me, just not understanding math and then like not spending time to raise my hand and ask questions, and just like getting moved along. Why? I'm sure there was no incentive to be like, those kids know math long enough. It's like, literally, I think it was like my junior or senior year. I'm sitting there with a math exam. Our math teacher had like a mental breakdown, so I had to like take the rest of the semester off or something. Don't get me wrong, I was a high school kid. I can see why some people may have had mental breakdowns. I actually had a number of teachers that apparently that did happen to. Um, Kids can be cruel, man. Kids can be cruel. I'm saying as somebody that was one at one point and slowly trying to grow up some 40 years later. But where are we now? Oh yeah. God, that was a whole bunch. Okay, so what was I doing? Let's go back over here. All right. So let's do our Planck friends. So this is just code data. You just type in code data and like whatever H bar, speed of light, something like that. All right. So for the speed of light, that's length divided by time. So elementary unit of length, we got 7 digits here because y 1, 3, 3, that's 7. Okay. times 10 to the minus 35 meters. So we got some error in the last two digits there, so we should note that. And then we got the blank time. The length divided by time. The elementary unit of length divided by the elementary unit of time. This friend over here also has 1, 3, 3, so a total of 7 digits. And again, we got some error there, so yeah, that could vary a little bit with that size error. Times 10 to the minus 44 seconds. That's a very, very small blip. Okay. So what I'm saying is, ultimately, we know about 5 significant digits to the time and length. So that's why when you do time and length, you only get about 5 significant digits. So you can only really say that. That is interesting. So let's see. Does this equal C? Actual exhaust speed. 1.8 furlongs per pico fortnight. That's one of the most fantastic conversions I've ever seen. Oh my god. The speed of light. If anyone asks you the speed of light, you just let them know. It's 1.803 furlongs per pico fortnight. And you're good to like 5 significant digits. Oh my god. Okay, so 0.29 gigameters per second. That actually sounds really cool. How fast is the speed of light? 0.3 gigameters per second, approximately. Oh, that convert on speed of light for Planck time for Planck length. Okay, now that is the normal speed of light, about 3 times 10 to the 8 meters per second. 63 astronomical units per year. It's about 3 times 10 to the 8 hertz per diopter. Oh, there's more. But wait, we got some more, my friends. Okay, so it's about 1 light year per year. Okay. 10, 10 estimated maximum black hole collision recoil speed. That's speeds. I've not heard that one. I've heard this one. I've seen this one. 0.01175 parsecs per fortnight. Oh my god. 1.803 terafurlongs per fortnight. God. Oh. Oh, yeah, we'll see. We'll see, Antoine. It, that's the thing. It's like the speed of light. What? It's about 300,000 kilometers a second, so 300 million meters. That's ridiculously far. I mean, we're operating on like that's actually really good for us because apparently, I know Professor Wolfram brings this up once in a while. It's like, all right, what if you were an entity the size of like the solar system? You're gonna move your hand and try to see you move your hand. If you're the size of the solar system, you're moving this. What happens if that mass is moving faster than the speed of light? Can you even keep track of your hand? Like how it so magnitudes matter. We happen to be fortunate enough that we're in about the meterish range. So that's kind of cool. As far as Planck constants, we're in basically the Planck momentum range, which is kind of crazy because it's like 6.52 what is it? Kilogram meters per second. Because it's speed times the Planck mass. Because we can just literally just hold on. Gigahertz meters, megahertz millimeters, liters minute per square meter. Oh my god. It's so many things. Hold on. I need to show you guys one thing. Planck intensity. This may have some of the greatest units ever. Hold on. There we go. Okay. Oh, do they have the other ones? Oh, is it not this one? Planck intensity. Hold on. I just view to the units. Does it have more? Oh, where is it? Watts per meter. There was there was something because there's one unit I think for intensity or some watts derivative or something where the unit is literally crabs. Hold on, crabs unit. There we go. A crab is 0.024 microwatts per square kilometer. What? Oh, it's 2.4 times 10 to the minus 8 watts per. Hold on. 2.4 times 10 to the minus 14 watts per square meter. Okay. So one, one, one mu watt or milliwatt times kilowatt square, if it's 42 crabs. 4 times 10 to the 7 crabs, 4 times 10 to the 13 crabs. Physical quantity. Okay. Frequency integrated spectral irradiance with respect to frequency. I think that just made my mind wobble. Microcrab, millicrab, sufficiently really, what is it? All right, so it's mass divided by time cubed. Okay, that's oh, so it's like energy divided by time? No, that's power. Because we did Planck energy divided by the Planck time. That'll give the third derivative of time, so that should be the Planck power. Yeah, Planck power. Okay. It's I only here's the thing. You learn this in like basic physics, just the dimensions. This goes to this, goes to this. For me, it's literally like, what is this thing? And just making mistakes and screwing up. And just like holding my head in shame and being like, why can't I do this? And then eventually it's like you do it long enough and it's like, okay, maybe you can kind of do this. But the whole purpose of any of this is to just show it's like there's a bunch of fancy stuff and things on the board. Okay. Some fun. I have some folks that I used to talk about and just yak with, and we did some banter and stuff back in the day. And then I'll see like a video, and I'll see like all the fancy symbols, and they're like, "Oh, like it means your GM." No, 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 no. It's just happen to have tools and having interests in things is important. Because if you don't have interest in something, you just look at it, you're like, I don't care about that fish symbol. It's kind of like me with like whether it was Common Core, the old school method, a lot of ways where they introduce folks to like math or logic. It's to be fair, math is logic, so they should probably just call it logic. And then we got some logic with some counting numbers, and you go into a different system. We could, I think, really do so much of a better job because it's like all due respect, because when they do the questions where it's like, if Timmy has 5 apples and Sally has 4 apples, and Sally gives Timmy 2 of her apples, all due respect to Sally and Timmy, I don't care how many apples they have. That's not what interests me. I care about tasty apples that I could eat or something like that. But it's you need to make it interesting. And if you could actually start incorporating things like, I don't know, Pokemon cards. Why? Well, if you have this many cards in your deck and you need to pull Charizard and you have all these other bonus Charizard cards, or I don't know how really that works. I just remember in vanilla Yu-Gi-Oh! It's like I got 3 blue eyes white dragons in my deck. I got 3 Lords of Summoning Dragon, 3 Flutes of Summoning Dragon, and a whole bunch of other dragon cards. As long as I can pull like 2 of these 6 cards there, I can basically like overpower and just like zerg through opponent's life points. And then you had all like the card destruction and just like the black holes and just like, oh, just gonna nuke the entire field and stuff. I think they started to get rid of some of those cards. Um, Let me just say, using that strategy does not work well in the current metas. I tried doing something like that, and then all of a sudden it's like in 3 turns, like 2 or 3 turns, somebody like did some servo replacement thing, and I'm like, all my life points are gone. Okay, I have no idea how to play this game now. It's yes, yes. We are turtles because everybody knows that.
World exists on the top of a giant turtle.
Why?
It's turtles all the way down.
You know,
turtles all the way down.
I do that mostly just so I can take a sip of water and just kind of keep continuing the whole little bit for a little while there. Well, see, that's the interesting thing, and you start. I'm not a biologist, but apparently during the like 2 hours, Wolfram was it in this thing? I think when he was talking about his proof for like the piano axioms or whatever, uh, he had said that he had found something maybe on the Wolfram Physics project, or maybe just while he was a physicist, kind of like the states on the boundaries of the states of matter, where like it's not like a solid, it's not a gas, it's not a liquid. And the way he was talking, it didn't sound like he was talking about a plasma either. So I'm like, it was like a boundary state where it could like shift into one of these other things. And I'm like, number one, I don't think I've ever heard that before. And then it's like, okay, well, it's still the same thing, but it's a different state. So is that one of Professor Jacob Barondos's emergibles that start to happen? Like, what is the threshold? Because apparently you see different thresholds for whether it's like superconducting properties. So basically, you're not going to have that thermal loss. So you could have, under ideal circumstances, basically no loss, power transmission. That's a huge game changer. That and actual like scalable fusion or other high yield style technology like that. Because I'm not saying that we do. Listen, China's up to like 1,000 seconds, like 15 20 minutes. I think it's like 18 minutes of like, all right, got a tokamak. We've basically got literal ring of fire going on, like hotter than the sun. We just got that chilling and working. Now, again, they still have to put in more energy than they were able to get out. You still need to harvest the energy and you go through that. But showing that you can actually do that, you're doing a proof of concept. So it really seems like it's becoming more of just an engineering feat. And if it's an engineering feat, that still means it's really difficult, but it means it's possible. Because if it's possible, then it really just comes down to human beings doing what they've always done, and that's figuring stuff out. Because that's the story of humanity, is to adapt and overcome, my friends. But all right, so I've been rambling for about an hour now, and okay, I think I got most of the stuff out of my head that we really needed. I think like we're running up to that point where it's have to have time to have a protein bar, peanut butter and jelly sandwich, like a glass of milk, so I can actually heal, and be back at you probably with this tomorrow. We'll be breaking the multiverse and some stuff and things, hopefully. I worry about that wolf girl. She is very, very silly. Where are we? Oh yes. Don't forget. I'm also a mun apparently. Monastery. Y'all take care.
Oh, yeah, I forgot
Well,
memes is a I said memes. Memes is a mun.
Yes, he is a mun.
I meant to say. You know what that works? That actually works.
He's a nun.
Memes,
Yes, he's a nun.
memes is a mun. That actually makes way more sense. Yeah, I like
Yes,
The
that.
soy sauce is kicking in.
Oh yeah,
Yeah, a mun, a
mun.
nun that
a man
that
nun.
identifies as a monk.
yes, I am a man nun. Now that you all know, and knowing is half the battle, Peace out, everybody. Take care of yourselves. It's a wacky and wild world out there, but there's hoping for a better tomorrow. And by better tomorrow, I mean today. Why? Because it's past midnight here. Peace out, my friends.